Well, good day. My name is Anthony Bly. I'm a soils field specialist with SDSU Extension. My office is in Sioux Falls at the Sioux Falls Regional Center. I'll provide my contact at the end of the slides here, so you can see that. Yeah, today I've been invited to talk about soil, of course, but I'm specifically going to talk about native soil nutrient supply and carbon basics. The native soil nutrient supply really isn't a hot topic, if you will, but did an interesting study with a student, and it's kind of thought-provoking, and I'm going to go through that, and then we're going to really talk about carbon basics today because of all the interest in the carbon markets and so forth, and soil health and building organic matter and what have you. But first of all, you know, I'd like you to get educated, and you're here listening today because of seeking knowledge and education. But you know, these are three really good books. There's others as well. I just can't fit them all on the screen, but these kind of present a progression that you should probably take on. First, you should start on the left there with the Soil Owner's Manual by John Sticka, and then move on to The Hidden Half of Nature by David Montgomery, and then eventually work your way to Dirt to Soil by Gabe Brown. And Gabe Brown's a farmer from North Dakota, and that's a very thought-provoking text there. So just three books, three texts that I think you should be interested in. So first of all, let's talk about that native prairie and cropland nutrient and carbon status. This was a project I did with an intern, Chase Staley, who's from the Mitchell area, belonging to Gene Staley and Staley Farms, and Craig is his uncle. But what we wanted to do is Chase is interested in sustainability, and so I helped him with this project along with John Woltheisen there, works for me. And a very interesting project. So our objectives were to compare the carbon and total nutrient status of native grass and cropland, a side-by-side comparison, because they had some native grass on their farm that's never been touched with any iron. And then we wanted to calculate the nutrient decline rate of the cropland based upon what we found in the native grass, and estimate that long-term sustainability. So what we did, we call that our materials and our methods. What we did is the location there is northwest of Mitchell. The soil has either been managed as native grass or in a cropland situation. And Gene estimated that it had been farmed for about 100 years, which 70 of those years was tilled and 30 were in no-till. We identified 3 sample locations on each management system, or on the grass side or on the cropland side. And we then sampled 5 cores at each one of those locations. And the soil depths we sampled are shown there. There's 5 of them in 3-inch increments there down to 6, and then a 6 to 12, a 12 to 18, and an 18 to 24. We also measured soil bulk density. We used the core method, and we only took 1 core per sample location. It's a very intensive measurement, very detailed, and it takes quite a while. So the soil analysis that we did on those samples, of course, is organic carbon and total nitrogen with the combustion method. And then we also measured organic matter by loss on ignition, and our total phosphorus, potassium, sulfur. They were measured by the nitric and perchloric acid digest. And then we also measured pH. So why total nutrients? You know, total nutrients aren't used in recommendations of fertilizer applications for crops. It's kind of an unknown status of nutrient in the soil. We don't teach total nutrients. Scientists, you know, it's been a long known fact that, you know, you can break down all of the minerals and clay and sand and silt in the soil and release all of those nutrients and measure it. You know, in the agronomy context, we only want to measure the nutrients that we know are going to be available to the plant. And so don't take this or extrapolate this into determining any value of your soil or the ability to predict crop yield, or don't relate that to any, because that would be improper to do that. But what's kind of driving this is the sustainability of our soils. And one thing that I've been doing in my professional career is tracking the nutrient removal of soil from our South Dakota soils. And here we see phosphate removed from our cropping systems over time. I was able to go back to 1981, and this on the y-axis is tons of phosphate, And so we can see in 1981 it was over 100,000 tons, and it's increased pretty steadily with an erratic nature due to climate, economics, drought, whatever. That's kind of reflected in there. Farmers have money or they don't have money is reflected in that. Big yields, low yields. And so now, in 2015, we're over 300,000 tons of phosphate removed from our South Dakota soil. So the blue line is the removed, and the red line is what we're applying. So you can see we're falling short in a lot of cases. So where is that extra phosphate coming from? Well, it's coming from the minerals in the soil. As they break down, they release phosphorus and the plants, and we are removing that. Okay. Another way to look at this is this graph I've superimposed is the phosphate leaving the soil. So I've basically combined, that's the difference between those two lines. And you can see at zero, there would be no net gain or no net loss. And most of those columns for most of those years are a loss, right? Because I put on there leaving the soil on the x-axis. So a positive number would be a loss, and a negative number would be a gain. So we've got about a handful of years there where we're making some gains. So this poses a thought that well, how long can this extra phosphate or phosphorus in the soil last? Is there a daylight when we'll run out of this? Our sunset, as you would say. So what we found is if we look at our total phosphorus measurements here in the 0 to 3, 3 to 6, there's those depths that we measured. We found that the native grass had higher total phosphorus at all depths except that 0 to 3. And the cropland was slightly higher in that 0 to 3 depth, and that reflects our fertilizer applications that we do in a timely every year, annually in most cases. So, but I think the important thing to note is phosphorus is being extracted all the way down. That native grass is higher than that cropland. That cropland, we're assuming, started at the same point the native grass did. That's our assumption because it's right across the fence, and that's what our assumption is. So when we measure, again, I kind of explained what total P is. When we measure total P, it's everything in the phosphorus cycle. Everything. We're measuring everything in that phosphorus cycle. And then just for kicks, I threw here on the left bottom corner, the different forms of phosphate given the different pH. So I want to just imply, or I want to show that the phosphorus cycle is very complicated. It's very complicated, okay? So we look at total potassium, K, total potassium, same depths here. We see that the native grass is higher in most all of them except down there in the very bottom depth. The cropland is slightly higher. That's just kind of variation, if you will. That's just a little variation. So we're extracting potassium from our soils as well. So potassium is released from the clay minerals as they weather, okay? And so basically as a soil ages, we call that weathering because it's subjective to our climate and to root activity and so forth. It's breaking down. Basically, larger rocks are becoming smaller rocks. That's about the easiest way that I can say that. And over here in the right-hand corner over here, you can see these clay layers, these clay particles. They have layers, and the minerals are trapped inside. And as they break down and these edges fray off, then those minerals are released into solution. And that's actually the cation exchange capacity right there. And then the plant roots can access those minerals. Okay, if we look at total sulfur, same story. More dramatic reductions from the native grass to the cropland. If we look at that graph in the upper left-hand corner, those blue lines are substantially lower than what I showed you for the phosphorus and the potassium. In the bottom right-hand corner, I have the organic matter levels, and we can see native grass is much higher at all soil sampling depths. Most drastically in that 0 to 3 and the 3 to 6 there. And so, it's kind of dramatic. Organic matter we know is the cornerstone or the keystone of soil life, and to see those reductions is kind of disturbing. But we know it's been happening because our families that came to South Dakota and started farming, they were probably the best miners that there's ever been on the planet. And I'm not laying blame with our ancestors at all, because I wouldn't be here if it wasn't for them, of course, and you wouldn't either. But they were making and itching out a living on those new claims and on those homesteads, and as they came west from farther east, as we filled in our country, and they were actually mining the soil. They didn't know it at the time, but that tillage was actually mining the soil. And so tillage does that to the soil. It decreases organic matter, or just cropping itself does that, decreases that organic matter. So we're going to talk a little bit more about that when we discuss the carbon. Here is the carbon. So we actually measured carbon at this site. We measured the organic matter and we measured the carbon. Same story as the organic matter, because carbon, the soil organic carbon, is a part or a fraction of the organic matter. So they would be related really closely. And then total nitrogen in the soil is related very well to the carbon content. For every 1% soil organic carbon in the soil, you see here 1%, there's about 1,000 pounds of nitrogen in the soil. And as we see carbon go up or down, that nitrogen also has to go up or down, because the carbon to nitrogen ratio wants to settle in there about 10 to 12 to 1. And so, so the total nitrogen in the soil is also being depleted by our cropland activities. Now, we all need to eat. I'm not saying that producing a crop is bad. It's just what's happening, and we want to show that. And it's related to sustainability. It's related to regenerative agriculture, and that's why I suggested reading those 3 books at the beginning of my presentation and progress your way along, because they're very thought-provoking. And while our generation probably doesn't need to worry about these things, at some point in the future, someone probably will. Here's the soil pH in that native grass and cropland comparison. That native grass is much higher soil pHs, really close to that 7, that neutrality that we really would like to see. Farming ground, in the high 5s and 6s isn't bad, but, we're on our way down, okay? And look at that cropland, just above 5 there in the 0 to 3, and then it goes up in the 3 to 6, and it goes up as we go down, of course, because our glaciated soils in the eastern part of South Dakota, it's a blessing to have those soils, because it ground up all those rocks and those minerals and that alkalinity that was there, that gives us that starting point in that native grass for that neutral soil pH, which is good. And of course, you measure bulk density. I measured that. Now, bulk densities, no more than a measurement of how much soil is in a given volume. Okay, this is kind of a scientific notation here, grams per centimeter cubed. So a centimeter is about that big, okay, and the cubed is a block, like a child's play block, except a very small one. So we're measuring the soil in each one of those little cubes, and it's just the way scientists do it. You have to accept that. But I think what you need to see here is that the bulk density is much higher in the cropland than it is in the native grass. And so it's more difficult for plant roots to grow through the soil, okay? It's more difficult for water and air to move in and out of the soil because it has less porosity, it has less holes in it, it's got more solids. And so that native grass root activity is really what's keeping that bulk density lower, okay? That living root there, the microorganisms that are there, the earthworms that are there, burrowing and opening up holes and letting air and water exchange in and out of that soil. Is this bad? Is this bulk density bad in this cropping system? Not yet. No, it's not bad yet. We like to see it right in this range right here. Okay, so it's nearing a problem, and we got to keep our eye on that. Okay, just to summarize a little bit about what we did here as far as sustainability of those mineral nutrients. I calculated how the level of mineral nutrients in the top 24 inches here. And you can see there's a lot, 3497 for phosphorus in the cropland, almost 17,000, 2,000 sulfur. The native grass is higher, of course, because we showed that on our graphs, right? Okay, so then I calculated the difference, what I call the native grass difference. So native grass has 470 more pounds of phosphorus, 1,133 potassium, and 733 sulfur. Now, we don't think of mineral nutrients in their elemental form. This is their elemental form, P, K, and S. So I converted those mineral nutrients to an oxide form that we think of more readily as what we have in fertilizer. We consider the analysis of the fertilizer in these forms here, the P2O5, the K2O, and the sulfate. So then this native grass difference is just transformed into these numbers. So the that was bad, Anthony. The 470, the 1133, and the 733 just converted into these numbers right here. Okay. And using that difference and knowing it's been farmed 100 years, then I calculated the rate of loss. Okay, the 100-year rate of loss right there. About 11 units of phosphate, about 14 units of potash, and 22 pounds of sulfate sulfur. So if you think about the longevity, this is really what we're after down here. How long can we go in this current pattern, this current land use pattern with our cropping systems? How long can we do that? Doing it the same way we've done it, applying relatively same amount of fertilizers, because this cropland is receiving fertilizers, and just keep doing that. Well, it's quite long. We can go 744 years, and that phosphorus will be depleted. 1,494 years on the potassium, and only 282 years on the sulfur. So, the soil is weathering, it is transforming, it is degrading. Basically, soil is geology, just in a different form. And so if we go back to those 3 books at the beginning, Montgomery especially and Brown talk about regenerative agriculture and the need to build soil. And so this really supports that notion that we really need to take care of our soil and to build it. Again, I said that our generations don't have to worry about this. we really don't have to worry about this. But at some point, problems are going to occur. And, we talk about phosphorus supplies in the world right now have peaked, maybe, just as crude oil has peaked. Other elements and nutrients can peak as well. That means their consumption reached a point where the supply affected the consumption, and now it's going back down. And so world supplies, the easy, readily mineable phosphate sources in the world are declining. And some estimates say that we only have about 200 years left. So if we consider that, that's going to even speed up this number even more quickly, because that will change our phosphorus application patterns. So let's focus on organic matter. Let's focus on carbon. Here's a picture of two samples right across a gravel road from each other, same soil type, same texture, everything the same except the management. The one on the right, at this time when I took this picture, 27 years in a no-till management situation. The one on the left, conventional methods, tillage, fall tillage. Alfalfa has been grown on the one on the left. It's been corn silage. It's been managed just conventionally, but you can see a big difference. The one on the left, lighter color, the one on the right, darker color. So what's giving that color? I usually ask the audience in a live situation when I can interact, what's the difference? And, most every audience has answered it correctly, and that the one on the right has higher organic matter. So we know that. We know that as a society. That's an intuitive deduction here, okay? But you can also see that the one on the right it's very crumbly. It's aggregated very well, and it falls apart like that native prairie, okay? And the one on the left is massive. It doesn't have that crumbly nature. The tillage has wrecked its soil structure, and it doesn't have the porosity that the one on the right does. So there's the importance of organic matter. I could stop right here, but I've got some more interesting things to say. So if we look at the relationship between carbon and organic matter, organic carbon equals about 60% of soil organic matter. If we just have an organic carbon number and we want to convert it to organic matter, we multiply by 1.66. Vice versa, if we just had an organic number and we wanted to convert it to a carbon, we multiply by 0.6, that factor right there, 0.6049. Okay, so they're very closely related. I mean, they are. They're right next to each other. So what's interesting is to kind of show this a little bit farther in the Staley study, which would be the orange data points here. There's a excellent relationship between the organic matter here on the horizontal axis, the x-axis, and the carbon here on the vertical axis, the y-axis. And it's just a line can almost be drawn through that data. Now, we've since done more work on a nutrient cycling study that I've been working on with a great team. And we also measured the same things, organic matter and carbon. And so I put that data set along or over the top of the Staley data set, and I fit the same line to that data, or I fit a regression line to its data, and it happens to be almost the same line. They're laying right on top of each other, okay? The cover crop data is more spread out, of course, and that's the variability we see because we're doing that work all across South Dakota, literally from east to west. Okay, but the relationship is still very good. It still fits that line. And so, wow, isn't that, I think that's totally amazing. I'm really happy to see that. And so this factor here is what we use to convert organic matter to carbon. soil organic carbon. Okay, they're slightly different at the tenths, hundredths digit and the thousandths digit, but they're pretty close. Okay, for science, for field science, you can't get any better than that. So let's just take a moment and look at the nitrogen cycle here. It's very complicated. We've got additions, we've got livestock, we've got atmospheric nitrogen, we're harvesting crops, we volatilize nitrogen, then it cycles in the soil, we got losses in the soil, we lose some to erosion. Wow, it's some people spend their whole life researching this topic. But if I superimpose the points at which carbon is instrumental in these processes, it's all over the board, all over the cycle. It's at every point. The cycle can't happen if we didn't have carbon, okay? So that's how important the carbon to nitrogen relationship is. And I just want to talk about that a second. I'm proposing let's manage the carbon to nitrogen cycle of the soil, and let's forget about CEC. We got so much discussion about cation exchange capacity. It's not about that. It's about soil health. We need to manage the carbon and nitrogen cycle. So ideally, 24 to 1 in that range. I mentioned a lower number previously, but it's in regards to where the microbes want it to be. But we keep it going and we add plant residues with carbon and nitrogen in there. We want to keep it up there so those microbes can keep proliferating and keep working. So the microbes themselves have about 16 parts carbon and 8 parts of that carbon is for maintenance. Crop residue, as we add back to the soil, vetches, which is a legume, has a very narrow carbon to nitrogen ratio, so there's more nitrogen available. The microbes consume that carbon, they release nitrogen. Wheat, on the other hand, has a very wide C/N ratio, 80 to 1. There's not enough nitrogen there to satisfy the microbial breakdown of the carbon. And so we immobilize nitrogen. We tie it up in those microbial populations. Corn's at 57 to 1, not as high as wheat. There's still not enough nitrogen there. So nitrogen is immobilized. Alfalfa, on the other hand, similar to that vetch, is 13 to 1. And as those microbes break down that carbon source, nitrogen will become available for plants. So this is what we're all after. We're all after getting something for nothing, or is it nothing? It's really not nothing, but we're after getting a big yield of corn with a low amount of nitrogen, right? Lot would say, well, I want that big yield without any nitrogen. Yep, that's what I'm after too. I'm after that too. So if we look at this return on investment here, we applied 55 pounds of N, which costs about 21 bucks. We got 35 bushels back, which are worth about $113. It gives us a 636% return on investment. Here's the cost. 26 years of no-till, 5.4% organic matter. Huge, huge. We can't get to this point unless we focus on carbon. I heard Dr. Lal speak yesterday, and happy to say, same message, same exact message. So we can't get there unless we focus on carbon. Another example of 2 independent studies across the fence: the blue, short-term no-till; the orange, long-term no-till. The orange is non-responsive to nitrogen application. The blue is responsive. So the longer we do the soil health practices and use diverse rotations and no-till, of course. I've quit saying no-till because I'm assuming everybody knows you got to do that. But the no-till, the diverse rotations and cover crops, we can get to this point eventually, but it takes a lot of time. Here's the Morrow plots, very famous plots in Illinois. Long-term plots established way back in the late 1800s, I think. And we can see the same story: diversity, more yield; diversity, more carbon; diversity, more yield, diversity, more carbon. So at this site, we got about 46 bushels of corn for every 1.5% organic matter. Okay, very important. At Mandan, North Dakota, same story. More organic matter, more yield. 13 bushels for 2.5% organic matter, 9 bushels for 1% carbon. Here we're at Chelsea, South Dakota, 25 bushels for 2.5% organic matter. Here we're at Garrettson, South Dakota, 58 bushels for 2% organic matter. Okay, very, very impressive responses to organic matter, to carbon. I give a huge amount of credit to Dwayne Beck for for being bold enough 20 years ago, maybe it was longer ago, I don't know the exact time, but saying we should be fertilizing with carbon. What a bold statement to make. And that's really what we're doing. And yesterday, Ratan, Dr. Lau, instead of NPK, it's really CNPK that we should be working with. We know that as we intensify tillage, that the particular organic matter decreases. That's just a given. This is study right here, Blanco and Yasa reference right there. We know that carbon is released from our tillage systems at different times of the year and at different rates. The no-till here being in the blue and the orange, okay? The tilled being in the gold to the green. Okay, so in the winter time, you know, the mower plow higher than the no-till, but you know, they're all low. As we go into spring, we do that tillage, we're releasing a lot more carbon. There's the no-till. As we get into summer, of course, those tilled plots go down from comparatively to our no-till, but the no-till is releasing it at the time the plants can use it. That's what is important about that graph. Higher for the tillage in the spring when the crops are small and it's just escaping into the atmosphere. It's risen in the no-till. In the summer when the crops are growing, the crops can hopefully capture that. So let's look at the crop type influence on carbon. I've done some calculating here from, I worked on this for a couple, 3 hours a few days ago. I got 3 crops here. I got yields, high yields. I think you'd agree. This is how many pounds of grain are produced with those yields. This is the pounds of stover, the plant material above ground. And then the pounds of roots are kind of elusive. That's an elusive number to find, but I found a reference I think is pretty solid. So I use their numbers to kind of calculate those roots. Now, pounds of humus per acre. Not all of those crop residues become humus or that stable carbon that we want. I've used the 20% number. That number ranges all over. I think it's a good number, but I think you're going to see them high. But anyway, about 800 pounds for the corn, 330 for the soybeans, and 424 for the wheat. These are the percent organic matter increases. And this is how many years it would take to get 1% organic matter increase. So I'm high. I'm just going to show you I'm high. It takes longer than that. So if we impose tillage on those numbers up here, the DeYoung, Hughes, and Aaron Day paper have organic matter losses here per year, and it's highest for the tillage and lowest for the no-till. We know that. If we would do the continuous corn, in other words, increase 0.222 organic matter per year, and lose 0.211, it would take 91 years to increase 1%. The chisel plow disc system would take 21 years to increase 1%, but the no-till only takes 5.5. Now, if we look at a corn soybean, a corn soy wheat, and a continuous soybean, we will never increase soil organic matter using tillage. Never. And in the no-till, 8.5, 9, and 17 years, respectively, to increase 1% organic matter. Now, how can cover crops and grazing increase this organic matter? Well, I've tried to take a look at this too, and there's some big assumptions here, but let's look at 1,000, 3,000, and 6,000 pounds of material. There's that much root. There's this much pounds of humus in the no grazing, and these are how much we're increasing organic matter. If we graze it, we're running that through a cow, and you can see I've used a 70% conversion factor here, what goes through the cow. We're increasing the amount of organic matter we can put out there. You can see the difference in these numbers. So the years to increase 1%, we can see here, goes from 71 years without the grazing to 40, 24 here for the 3,000 pounds to 13, and 12 to 7 for the 6,000. And down at the bottom here, I've shown that calculation for that 1,000-pound rate. Here's the cow, and here's the remaining stover. They come together, and we got that number right there. So I just put that in there for reference. So what's actually happening on the farm? Here's a Southeast South Dakota farm. This is real data, organic matter data. No-till since about 1990 right here. And you can see increasing organic matter, okay? And so that long time period, about 2.4%. From 1994, I did 3 comparisons here, about 1.8%, and then in the last year's almost 1%. If we look at the carbon, what is that worth in that no-till? I converted those organic matter numbers in this slide using that equation that I showed you to carbon in this slide. And so I converted those soil organic carbon numbers to CO2 equivalents, how many tons. So over that time period, this farm has sequestered 53 tons per acre of CO2. If I use a $100 value, that's $5,300 of sequestered CO2. The $100 value is under debate. You will see numbers from 10 to 200. So I just had to pick one. Now, if we go to Central South Dakota, this is a mess, but this farm thankfully did a bunch of zones. So I've calculated the organic matter change based on each one of those zones. That zone down the bottom that's very wet, that deep swale that only produces a crop 1 out of 5 years or 4 years, is losing carbon. So the carbon increase there at this long-term no-till farm in Central South Dakota is much lower than the long-term no-till farm in Eastern South Dakota. So what's the difference? The Eastern South Dakota farm is a tall grass prairie. That's what the native vegetation was. And the native vegetation of the Central South Dakota farm was a short to mid grass prairie. So that's the difference. So here are the soil health principles: keep the ground covered, grow living root, use diversity, use no-till, and try to integrate livestock. So in summary, all nutrient, carbon, and pH levels were higher in the native prairie, except the phosphorus in the cropland. Soil bulk density was greater in the cropland soil. Carbon and total nitrogen are highly correlated. Total soil nutrient supply has finite limits if we really think about it. Soil organic matter carbon is vitally important for soil productivity. Carbon loss is minimized by reducing tillage, using crop rotations that add high amounts of residue, maximizing productivity by managing soil nutrients with fertilizers and manures, avoiding crop residue removal whenever possible, and using livestock to cycle those above ground plant residues. The soil carbon and nitrogen cycle is very complex. Focusing on building carbon is the most important issue. The soil nitrogen cycle can be built large enough to reduce reliance on commercial N. Don't run out and do this next year, please. I want to do no harm, but eventually that should be your goal. And maybe in 30 or 40 years, your farm can attain that level. maybe it can do it more quickly. Just get on the road and learn and read those books and listen to Dr. Lau and Gabe Brown and Jimmy Emmons and Dwayne Beck and everybody else. I can keep naming names. Just go listen. Cover crops are a tool to do this, okay, along with grazing. So with that, I'm done with my presentation. I'm actually tired of talking, and so hopefully you've found some tidbits of information in there. Here is my contact information. This is my office phone number. Please call. My secretary, Jen, will get me in contact with you as quickly as possible. Here is my email. Please feel free to send me an email. Well, again, thank you for your time today. Thank you for your attention in this important topic. I'm sorry I couldn't meet with you in person. I really miss talking to a live audience. The COVID pandemic has caused a lot of changes that we've had to endure. And so I think there's a lot of hope for 2021, and I hope to get back out and visit with more of you around the state. And as we're working in the fields, if you happen to see us, please say hi. So thank you for your time.